Okay. So I'm going to take as my starting point the physics that we know and know quite well in the context of, say, the LHC, even cosmology, pretty much everything, semiclassical space-time, and local quantum field theory. And of course, we know that when these are applied to a black hole, we get a story where the black hole evaporates and eventually reaches the Planck scale, where presumably it disappears. And in the process, you end up building up a large entanglement between the black hole and its environment. The entanglement grows monotonically, just automatically by virtue of the Hawking process, completely naturally, because of the pairs where you have one partner go out to infinity, eventually, well, in the end, asymptotically turning into a Hawking particle. And also, you can, of course, increase the entanglement sort of artificially by, say, making EPR pairs and throwing one partner of those pairs into the black hole, and that also monotonically increases the entanglement. And, of course, if the black hole completely disappears, you have a huge amount of missing information or entanglement with things that are lost. Unitarity is violated, and we're in trouble. So everyone basically knows this. This is just a quick review. What we need to do, many of us think, is save unitarity in quantum mechanics. And in order to do that, it looks like what we need to do is transfer this entanglement from inside the black hole, in whatever sense that's defined in the full quantum theory of gravity. We need to transfer that entanglement from the, say, from the black hole states to the environment before the black hole disappears. Of course, local quantum field theory does not allow this by the basic property of locality. Once you have some information inside the black hole, say there, it can't escape in the usual story of local quantum field theory in a semiclassical background. So the big problem is to understand how semiclassical space-time plus local quantum field theory can be modified to fix it up and end up with a unitary story. Again, assuming that quantum mechanics ultimately is part of the fundamental framework of nature. Okay, so that's our goal, is to find a more basic physics that satisfies a few criteria. First, it should match local quantum field theory in, let's say, ordinary circumstances, LHC, condensed matter, experimental labs, et cetera, et cetera. In particular, it shouldn't violate locality in ordinary circumstances. And so this is a statement of basically a quantum gravitational correspondence principle. Secondly, we would like to save quantum mechanics. So in the end, we want something that really does build in unitary evolution, or have a unitary S matrix, say, if you think about scattering in an asymptotically flat background. And finally, let me invoke a principle of conservatism. Often conservatism is the right way to approach physics to sort of do the minimal necessary damage to the structure you already have. In this case, the semiclassical picture. So that's how I look at it, what we're after. And I'm going to at least outline some possible general properties of such a physics in the context of black holes. So, any questions so far? I even got past my name and 2 slides. This is a new record. So, yeah.
So is it clear that the information actually needs to be transferred from inside the black hole, or suppose it was at some point deposited on the stretched horizon? And then
Yeah, if it never got in, that would be an alternative. If there's some sense in which it never got in, but that's that goes back to things like, for example, the complementarity picture we certainly, at least if we're close to local quantum field theory, we do have a picture where we get in. We can fall into a black hole and carry our information in.
So maybe a related question is then: should there be one global perspective on which everyone agrees on, or is there still an objective or a subjectivity where one perspective gives a different semi-classical picture and then another perspective?
Let me try to partially answer that. If we're talking about quantum mechanics, we might take the viewpoint that at least there's one Hilbert space, period, for the whole system. And then there might be different ways of writing down observables that, say, correspond to what people outside see and what people inside see, and so on. Now, at least in local quantum field theory, you can easily reconcile those. And so you might expect that you can still approximately do that, but there's some corrections. But maybe it's a much more radical departure. That's one of the things that's been proposed. But I'm going to try to do the least damage possible.
But say when we are talking, say, about this Hawking radiation, if corresponding scale is of the order of the size of the core itself, then maybe that's the very notion of separation inside and outside could be broken.
Well, yeah, and I'm actually, in some sense, headed in that direction, but the question is how badly broken, perhaps. And so we'll get to that, I think, at some level. Yeah.
So the picture that Samir had yesterday, where indeed things sort of start tunneling into other degrees of freedom when you start approaching the horizon.
Yeah, well, when you reach,
a large disruption of the semi-classical picture.
Well, that's where there's obviously debate and discussion. To summarize at least some, sort of version of yesterday's discussion, there's something like Planck scale structure at the horizon in the fuzzball picture. And naively, you might think that, you hit that and you die before you reach where the horizon would have been. But Samir is proposing that there's an alternative, that there's some sort of dual picture where you can sail through and still feel like you're yourself. And so that's even another iteration on things where sort of a miracle has to happen. That was part of the discussion. How could that miracle happen? Okay, so what are some possible general properties of this in the black hole context? And so let me start with the just basic picture of what I call nonviolent nonlocality. And so what are its characteristics? So first of all, I've shown, actually it barely came through, but you can see it, a shaded blue region that extends outside the horizon. And the idea is that local quantum field theory is perhaps approximately true in some sense in that region, but there are corrections to local quantum field theory on the background in that region. So specifically, the first characteristic is that we need information transfer from inside the black hole. Say if we take the semi-classical viewpoint, then you might think the information is concentrated in some sort of core of a black hole where you really reach something approaching Planck curvatures, but that's not absolutely critical. The important thing is information needs to transfer from the so-called inside degrees of freedom to outside degrees of freedom, and so somewhere in this blue region, and then ultimately that information will escape to infinity. So that's the first idea. That's the but that does represent something that is non-local with respect to the semi-classical geometry, as we've just discussed. This would be forbidden in local quantum field theory. But that apparently, something like this or something even wilder is needed. Okay, so that's the first word of the title. And what about the nonviolent? Well, there's a question of scales. For example, you could have the AMP story where you have non-locality reaching out just to the horizon plus or minus a Planck length, and you could transfer to degrees of freedom that are Planckian, and that's one possibility. But the nonviolence comes in assuming that you have transfer to, say, degrees of freedom on characteristic scales that are, say, L, outside the horizon, where L is bigger than the Planck length, could be, say, a power of R, but something that, say, grows as the black hole grows. And so you have both transfer to this larger region and to, say, degrees of freedom with longer wavelengths than, say, Planckian. And so another way of putting it is this is a soft or a softer transfer. It's transfer to softer degrees of freedom rather than the hard degrees of freedom. And that's the explanation of the term nonviolent. So this basic proposal has been explored in a series of papers. It may be what these folks in the end are trying to say as well. I don't know. I'm not going to address that. But that's the basic proposal for how things work. Tom.
So, Steve, when you say scales, there's a sort of issue of, are you talking about length scales, or are you talking about energy scales?
Not just
scales?
frequencies,
So
because we know they're...
in invariant systems, those things are all connected together.
Yeah.
But
the black hole sets a frame.
Here.
It sets a frame, and even more than that, there's a...
So you're talking about length scales when you say this.
For example, it wouldn't suffice just to say we only transfer to small omega modes, because we know that they're very short wavelength.
It depends on whose omega you're talking about.
Right. Well, if it's Schwarzschild omega, that will not do, because we know they're very, very high angular momentum, high wave, or
but what
high
about
wave
this
number.
characteristic frequencies associated with Hawking radiation? Because they looks like relevant to what you're saying.
Yeah, so one example would be p equals 1, and that's the simplest possibility. And that's one we will actually, think that's the simplest thing, so try that
because
first.
it sounds related to radiation, right?
Yeah, another way of putting it is the black hole gives you a scale unambiguously, that's r, the radius. So, maybe it's used in other ways by the physics, and that's a quite natural hypothesis to explore. That will come into this story. Okay. So that's what I mean by soft. And another way of putting it is, this is excitation of the degrees of freedom in the atmosphere of the black hole that an infalling observer, say in a really big black hole like the one at the center of our galaxy, they may see something happen that's unusual. They may see some extra quanta, but they don't get burned at the Planck temperature, for example, like the firewall story. So that's the contrast. Okay, and I think I already said the non-local transfer is shared by a variety of scenarios or other kinds of non-locality. For example, the firewall scenario, as I said, does transfer, or at least the simplest version of it looks like it transfers just to the horizon. Another way to state this is if you think about the basic postulates in the complementarity paper going way back that AMPS also adopted as their set of postulates, namely unitarity, that semiclassical field equations hold outside the stretched horizon plus a Planck length. The black hole is a quantum system with a number of states given by the Bekenstein-Hawking entropy, and the free faller sees nothing unusual crossing the horizon. This already says just outside the horizon, basically. If you look at these postulates, the postulate that really is primarily being violated, or at least that I'm proposing to violate, is postulate 2. There's some corrections to semiclassical physics in the immediate vicinity of the black hole. Specifically, information transfer is allowed over this characteristic scale L. Okay, so
Steve, if I try to think about the Hilbert space or the operator algebra associated with some causal diamond of size of this characteristic scale L.
Yeah, many tricky things come into that.
Which is something we could talk about in quantum field theory, right?
Well, in quantum field theory, that's right. Yeah.
So in what sense do you claim that you're not violating quantum field theory? Is that Hilbert space or operator algebra roughly the same as the one in quantum field theory? Does it have infinite dimension?
That I'm not violating. Well, sorry, I am violating I am modifying local quantum field.
But sort of by a little bit, right?
Well, yeah. So the question is, what is a little bit? And I'll come up with more specific models. But the idea is that say if you write down the Hamiltonian, say in some slicing for local quantum field theory describing the semiclassical evolution of the black hole, it just will not transfer information from inside to outside, right? It just cannot do that.
I understand that, but in what you put in place of quantum field theory,
Yeah.
what are you thinking of the Hilbert space as? How have you changed the Hilbert space as compared to quantum field?
Yeah, so I'm thinking more, the answer I was going to give is I'm going to change the Hamiltonian for now.
Yeah, I think he's not changing the Hilbert space.
And I'm still...
He has nice slices, right, with commuting degrees of freedom.
Well, okay, there's a cartoon of this, and for now this is only a cartoon because there's something I am confused about. There's a cartoon that the Hilbert space just factorizes, and there's a black hole Hilbert space for the inside, and there's the exterior Hilbert space for the outside, and that's like in local quantum field theory, although again there's issues with that. That's not precise. But then the evolution, which, if you wrote down the usual Hamiltonian evolution, it wouldn't transfer from inside to outside. It just doesn't, if you look at the Hamiltonian. Then you, however, consider corrections to the Hamiltonian that do transfer from inside to outside. And so that's the simplest version of it. Again, that's a cartoon because of this whole business of how to, A, you can't factorize the Hilbert space, and B, as and this is earlier discussion, it's not even clear how to find commuting subalgebras, although that may be part of what's going on here, ultimately. Okay, so how would this arise from a fundamental theory? And this also is related to the question I was just trying to answer. Well, first of all, we don't yet have a complete picture. But what I'm saying, at least sort of morally, seems to dovetail with this statement that we seem to have reached, that locality is just not sharp in quantum gravity, and there are puzzles about how to really think properly about locality in quantum gravity. And if that's true, then you might think that by the time you figure out what's going on, if you try to describe things in the local quantum field theory picture, you might have what amounts to sort of non-local corrections to the local quantum field theory story when you finally reach your complete picture. Maybe this all comes from ADS-CFT somehow, if and when we actually understand in detail what ADS-CFT is telling us, and that's been one of the big challenges, and we've had a fair amount of discussion about that. So that's one possibility, and I think that's the approach many here would like to take to all of this, is start with ADS-CFT, see what you get out of it, although, again, many challenges there. Another viewpoint on this, though, is that maybe what really the black hole is giving us is a key guide to the underlying principles. And what I have in mind here is like the story of the history of quantum mechanics, where there was this thing that needed to be explained, the atom. The existing framework did not explain it, classical physics. And we didn't just start with the principles of quantum mechanics. We started with phenomenological models, Bohr did, for example, that captured the right physics at some level, and then we had to eventually figure out how to put that all together into a consistent set of principles. And to me, it seems plausible that that's how this, in the end, will evolve. Maybe we will get it all out of ADS-CFT, or maybe it'll be some combination, but this is an alternative path that has certainly been followed by the history of physics. Maybe the black hole is our hydrogen atom. Okay, so in terms of how to think about the small corrections, can we model those as a modification of local quantum field theory? And so there's more detailed discussion in the references here, but I'll talk about that a little bit. And once you do start to model the corrections, you can begin to test the picture and see what sharp constraints are there on the story. Are you forced to have a firewall or something even more radical? Or is there a way out? What do we have to give up? We know we have to give up something from the local quantum field theory plus semiclassical space-time picture. And are there observational consequences. Sounds wild, but you should think about everything. One point I want to make is I think we should avoid double standards. And so, I've already said there's, not a completely fundamental theory that I'm starting with here. And that's a possible, upfront objection. Or, you might say, well, I can find problem X in your model, therefore there's a firewall. And there's been a certain amount of the reasoning in the field that has basically gone that way. Well, that's fine, but we don't have a fundamental theory or complete model of firewalls either. And if people started to write them down, I expect there'd be some very, very serious objections, trying to write down something sensible that looked like a firewall. So, let's keep the same standards. And in my view, what we should be trying to do is infer reasonable physical behavior by making more detailed models and exploring the constraints and the challenges and the problems. And we should try to see if there's a sharp argument against these models on reliable physical grounds, or whether, in fact, there's a path that nature could take there. Again, the unitarity crisis tells us that we have to give up something, and our job is to figure out what it plausibly could be. And by the way, you could say the same, I think, as we've seen in the discussion. You could say the same here for, say, ER equals EPR or state dependence. There are a lot of debates. We don't have a fundamental theory, really, that yet, I think that at least people agree, makes sense and describes those approaches in full consistency either. Okay, so in that spirit, phenomenological models, again, stress on models, not yet theories. So one way of picturing things is I'm going to assume that semiclassical spacetime and local quantum field theory are the starting point, but I've got some corrections. And let's just think about breaking things up somewhat artificially at, say, half the Schwarzschild radius into internal degrees of freedom. This isn't necessary. Perhaps this region extends out further, but let's say half the Schwarzschild radius is where the internal degrees of freedom lie within, and then degrees of freedom that lie outside. And so we imagine, as I already mentioned, modifying the Hamiltonian or the action. And let's imagine that in this sort of effective phenomenological model, that there are some extra terms in that Hamiltonian of the following structure. So first of all, there are operators here, OA, which are operators that act on, so to speak, this Hilbert space. Again, in quotes when I say Hilbert space because of the various issues, but that's the picture. Then there are operators here that act on the Hilbert space further out. Could be outside the horizon as well as inside the horizon. Have to at least be outside the horizon for what I'm saying to hold. And then, so there's some operators, and these you might even think of as basically operators of local quantum field theory, which is a pretty good approximation, say, out here. These act on the black hole Hilbert space, so they may be much more, they may not look like local quantum field theory operators. And then there's some...
R is the Schwarzschild coordinate, little r.
Yeah, that's right. And then there are some couplings between those operators that depend on which operator you're talking about inside, which operator you're talking about outside, and also have some space-time dependence outside the horizon, which gets integrated against the operators that live in the vicinity of the horizon. So those are some coupling functions.
Should this point actually be right at the horizon, or can it be further out?
No, this integral is over, I said, over r bigger than r over 2, and then the question of where these really live is the question of the functional dependence.
Yeah, but once you have some kind of exchange, normally we would associate it with certain field or whatever, and then we are back to the square one, right? Because why this field would not... because usually it's interpreted in terms of local field theory as an exchange, right? And you are trying to avoid this.
No, this is something that it's important. It exchanges information, in fact. It's an interaction, but it's an interaction that doesn't, in one way of putting it, respect the usual causal structure of the semiclassical space.
So it breaks causality in this sense.
I'd prefer to say locality. I don't think it fundamentally breaks causality, at least not on sort of large scales. Yeah.
So you could also write down an integral that only involves time-like or non-localities, right? And it's essentially non-localities outside of the horizon. So that would really keep causality, but it would.
Well, I think, again, I don't think this necessarily violates causality. That's somewhat of a separate distinction.
It breaks, say, like a Lorentz invariance, right? Because it's only or space, right?
Wait. No, X is 4-dimensional, say, if we live in 4 dimensions.
It's 4-dimensional.
Yeah. And the reason it doesn't break locality, sorry.
You're calling this delta H, and Hamiltonians are usually given by 3 volume integrals.
Yeah.
Oh, sorry.
4 volume.
Integral dt of delta H. The reason it doesn't necessarily violate causality is because the black hole sets a frame, and so we can't turn space-like propagation necessarily into backwards in time propagation. Say if we have a bit that goes in here, and one way of putting it, hits the core of the black hole, stays there for a long, long time, and then comes out up here. That is something that asymptotically is purely, well, it's causal. There's a big time delay, and there's no way to turn that into backward in time propagation. And that all comes from the fact.
OA is not, is that?
What's that?
OB is local, but OA is not?
Yeah, so at least in these simple models, you think of OB as being, say, a local field operator acting here.
Right.
And OA is some kind of operator that acts on the internal Hilbert space of the black hole, say, acting here, so to speak. So it's,
Not at a point.
What's that?
Not at a point?
No, because I think that, let's phrase it this way.
Well, you don't have to justify it. I just wonder.
Well, let me just phrase it this way. So at least the most conservative thing is local quantum field theory is really good far from the black hole. It's a very good approximation, like in this room. You start to see some violations of it here, but we pretty strongly suspect local quantum field theory doesn't work very well, here. And so that's why I don't think of that as being a simple local.
So this acts on your black hole Hilbert space, which has no quantum field theory description. Is that right?
At least it's not obvious that it has to have a local quantum field theory
So
description.
why can't I think of OA as living on the horizon, in which case there's no violation of causality?
You could probably, you could probably choose a gauge in which you describe things that way. But I think implicit in the statement that you could say approximately have a local quantum field theory description all the way down to here is the statement that you could also choose a gauge where you have basically local quantum field theory evolution, maybe with some corrections down to smaller, you could sail into the horizon and still use local quantum field theory, at least approximately. So that's something as well that at least I'm trying to capture, is that you could have a gauge where that's fine.
Steve, is it possible to use this addition as, let's say that it's like instantaneous interaction, and integration over time is just overall, so in Hamiltonian it would be just instantaneous interaction the way you are describing there, right?
Well, so what's going on here? So this integral is, so I'll write down more in a minute, but you might expect that, say, these combined operators here, if you look at matrix elements of those in black hole states, they have some support that is over, say, some region that looks like this. And so they can basically interact with degrees of freedom here and, say, transfer information to degrees of freedom here, and then it escapes asymptotically as ordinary particles. So it's
essential that you have a large time delay. Yeah, that's,
you mean
for construction. Is that important?
Well, I certainly don't want it to, I don't want time advance, and you might expect there's a large time delay because, the leading semiclassical approximation tells you the information never gets out, so a small correction to that might say it takes a while to get out. But, you want, let's put it this way. I think you need a time delay that's at least of order, say, r log r to avoid the paradoxes that were talked about in the context of complementarity. But maybe it could be as short as that. So, Jim.
So OA is defined on some slice in the interior?
OA is defined as acting on the Hilbert space of the, we think of the Hilbert space as being factorized. Again, that's a cartoon.
Well, I'm okay with that, but it's the integral D3V. So you're
Oh,
integrating
dV4, this integral? Is that what
you're
you're
integrating over time or not?
This integral is over that x and that x.
Which includes time.
Which includes time. Yeah, I should have written an integral
Sorry, I
dt.
didn't understand the notation.
Yeah.
So when you say delta S, you mean the change in the action?
Yeah, this is delta S, and this should have had an integral dt. Okay, so that's the basic picture.
One more technical question. This term includes capital A, little b couplings.
Yes.
But no little b couplings.
Yes.
But if I were to say, well, I don't really know what the OAs are, I'm going to integrate them out or something, that would generate little b coupling.
Yeah, I'm not sure if you could really we can't always integrate things out, at least unless you go to long enough, say, time scales, and maybe there are big time delays here and so on.
Another way to phrase my confusion, if I were to change r over 2 to 3r over 4,
yeah.
Which presumably you're going to allow me to do.
Yeah, that'd be maybe something like choosing a different gauge. So the Hamiltonian may look different in that.
But the difference, the difference between those two would involve B couplings in this language.
Little b, yeah.
So how dedicated are you to this form with only A, B couplings?
Yeah, so potentially that starts to drive out, the question of so to speak, loop corrections is one way of putting it. It starts to drive out, what is the more fundamental theory? And yes, there should be a story there. No, it isn't worked out. I'm trying to model, what what could be reasonable physical behavior. But yeah, ultimately that kind of question should be answered.
I'm glad you're writing down formulas, which is more than some people in this business do.
Right. Trying to.
But what you're describing then would be something where this term could also lead to an absorption of something into a non-local absorption.
It could, and so the obvious concern is, well, okay, what if it's a big non-local absorption and that is a big correction? But if this term is, let's phrase it this way, if this term is doing something like transferring quanta out, comparable to the rate at which Hawking particles are emitted, that's a small effect as compared to the leading order effect for infalling stuff. The leading order effect for infalling stuff is it just falls in. That's an order 1 amplitude for it to just fall in. And so this would be a small correction to that. Okay, so simple examples. First of all, we could lump all of this together, the OA and the coupling functions, into just something I could call J, a quantum source. It's basically, it acts on the internal Hilbert space, so it's a quantum operator. And so that's what I mean by these J's here. And you could have something that, say, just couples linearly to a scalar field. Again, J is an operator acting on the internal Hilbert space. Or another nice kind of coupling is to the stress tensor in the vicinity of the horizon. And then, these, again, are quantum operators, but you might expect that in some appropriate superposition of black hole states, they basically behave like classical sources. Just like when you have a radio antenna emitting radiation, ultimately there's a quantum operator coupling the radiation to the antenna, but you can approximate that by a classical source for many purposes.
So J here stands for this, comparing
this.
The sum over A of
yes.
OA times GA.
Yeah.
So the part of the integral that's inside the horizons cannot transfer any information out.
Yeah, I could have just written this as an integral from R equals R, but that looks a little funny. And certainly you could imagine that there's sort of smooth transfer of information over a scale of order R, and if it happens to transfer to here, it just falls back in, basically. So that doesn't do anything. So I'm just allowing for that, basically.
But then in this form, Okay, let's say that there is a kind of real singularity at r equals 0.
Well,
it's a point like and it acts on phi. No, I mean, when I look this, I can say that there is a source which is associated with singularity sitting at 0, for example.
Yeah, but that won't have this structure. Say this really is an integral not down to r equals. I'm saying that j of x has support, needs to have support outside the horizon. Otherwise, you don't transfer information.
Steve?
Yeah.
So would it be correct to say that instead of spending a lot of money to find out whether there's a black hole in the center of the galaxy, I could...
Don't jump ahead. Don't jump ahead.
Oh, sorry.
I hope to get there by the end of the talk. If you're going to ask about looking at the black hole in the center of the galaxy.
I was going to ask whether we could in principle detect it from local observations that there were black holes. Somehow.
Save that for the end of the talk, assuming I make it.
Thank you.
Yeah.
So I was just wondering, maybe you already answered this. If I take the good slicing of the black hole where I don't see anything going wrong till...
You mean the nice slices?
Singularity. Yeah, the nice slicing of the black hole. Then how would I justify that these operators should kick in, because it looks just like, just like I have around here? Or will they always kick in?
Yeah, if you had a nice slicing, I think that we have pretty good reason to believe that the nice slicing doesn't give an accurate description of the Hilbert space and dynamics beyond a certain time. And there are
some criteria that, okay, if this happens to the slice, these operators will kick in.
One could try to do that. Yeah, I think. I'm not going to do that here, but that is, I think, it seems to be one of the morals is that we could try to describe dynamics on the nice slices, and but ultimately that gets us into trouble. And so there's something wrong with describing the dynamics in the Hilbert space in that slicing, and so we expect big corrections at a certain point. And the question is, to what extent could you detect those corrections by doing, say, quantization on those slices? That I'm less optimistic about. I think there's basically new physics that needs to come in.
So maybe I could rephrase the comment this way. I've written something some while ago, and I think you also wrote about these things at some point, that in the nice slices, they look smooth, but they are becoming long.
Well, yeah, you could ask. You could ask
what. Could be a criteria where something happens.
Well, yeah, what's wrong with the nice slices? And I think there are different possible versions of that story. And although, well, for example, there have been arguments that something's wrong at the r log r time scale. And I think there are other arguments that there's something wrong on the r cubed time scale. Right now, I don't feel like I need to commit to those, but the bottom line is that eventually there's something wrong by the r cubed time scale, and so that new physics is needed to
but sort of
correct.
You need that in the argument somewhere, right? Because you can always say a new operator will kick in, but you've got to say why it doesn't kick in the galaxy but kicks in there. So.
Well, yeah, and that comes into the question, two questions, and I've said a little bit more about those questions in various papers, but two questions. One is sort of gauge dependence, because you could choose a slicing that stays outside or goes inside and is nice with asymptotics to a given inside radius and different inside radii. Those are different gauges. So the question is, how do you describe the relationship between those different slicings or gauges? Because again, one slicing just stays outside the horizon. And then it's also a question of the more detailed dynamics ultimately describing, say, these degrees of freedom, which again, I'm staying agnostic about because, or at least I'm not stating precise statements about, because the important thing for now is what can be seen outside, and the question of whether we have to have big modifications crossing the horizon. What goes on down here isn't particularly germane to that, I don't think. So that's the attitude I'm taking. Okay, so those are the interactions, and these interactions transfer in information, or entanglement is one way of thinking of it, from the black hole to its atmosphere, and then it escapes in basically usual local quantum field theory excitations. Now there's a challenge with this kind of picture, and that is that you generically, unless you disrupt the Hawking process, well, that's going on, and that's transferring energy out of the black hole. In addition, you've got some process that's transferring information out, and so that's basically going to, you expect, transfer energy out, so you'll have a flux of energy going out that's bigger than the Hawking rate. The black hole decays faster.
Why wasn't this just an effective way of describing the Hawking process? Because you also want to have that as on top of it.
Yeah, no, the Hawking process can be described, but it's not quite the same form. And so this is, in addition, I could have written the local quantum field theory Hamiltonian in a slicing, and it would have included the Hawking process, and it wouldn't have looked just like that. We could come back to what it looks like, but it wouldn't have looked just like that. In particular, it wouldn't have transferred information. These kinds of interactions can. And so, anyway, this is a different kind of term in the Hamiltonian, say. Okay, so generically, you have extra flux of energy. And that raises at least a concern. That means that if you try to equilibrate a black hole in a thermal bath, well, this suggests that you will have a higher temperature equilibration, so a smaller entropy of the black hole than given by the Bekenstein-Hawking entropy by detailed balance. And so that, well, that's something to ponder. Either we've got to find a way to evade this statement and find some special evolution with just the Hawking energy flux, or maybe we'll find some no-go statement that we can't do this. Or we've got to make peace with this, that the Bekenstein-Hawking entropy is not getting the right count of the microstates. Or we have to do something else, say accept a firewall or something more radical. And I consider many of the alternatives on the market, all of them I consider more radical. Anyway, but these are important questions. How does,
How can that work in equilibrium? Because you get temperature from the Hawking calculation.
Yes.
And then we basically from that we can derive.
Well, again, I think it equilibrates at a higher temperature. And that's because there's extra flux coming out. Now, all of this is going on at roughly wavelengths comparable to the thermal wavelength. And you could try to ask if you can get yourself into paradoxes. And that's a good question, actually.
Because then already you're violating the semi-classical physics in some,
well,
I would say, order 1. Because if the temperature is of order 1 different, what's the same?
Well, yes and no. Yes and no. The semi-classical geometry may look like the, say, the usual black hole geometry. I guess, well, I was going to, well, maybe I should come back to this, but, you can have systems that effectively have 2 temperatures, and, you may have the semi-classical geometry, but something going on in addition to that, basically.
Well, actually, let me ask, so the Aaron Walsberger question here, which is...
Can you make a perpetual motion machine?
Well, yeah, it's the zero, you're violating the 0th law of thermodynamics, right? If you have a system where one part of it is at one temperature and another part of it is another part temperature, then it can't really be an equilibrium.
Well, the question is how do these equilibrate? And, I know that people consider, for example, the eternal ADS CFT black hole to be...
That would be an example where it would be very surprising.
Let me finish. Okay, they consider that to be a simpler example because the geometry is simpler and various things are simpler. But in some ways, a black hole in a thermal bath is a more complicated thing. And so, another thing one could say is, let's think about just the sun. Okay, the sun is 6,000 degrees, right? You could go, sit in the photosphere and it's 6,000 degrees. There's some equation of state, blah, blah, blah. Well, not true. It's not in thermal equilibrium. It looks like it's in thermal equilibrium, but there are other things going on. For example, high energy neutrinos streaming through you. So, okay, so there are something more complicated than 2 temperatures. Now, if you try to equilibrate that by putting it in a bath, that may look somewhat different. So there is a question of what it looks like when it equilibrates, I agree, and that's something to think through more sharply, ultimately.
Steve, how did you prove this dE by dt is bigger than the dE by dt Hawking?
I didn't prove it, but it's a generic feature you observe is the kinds of couplings I wrote down. Basically, if they're transferring information, they're transferring extra energy out. And so one could, I think there's...
You can't partially disrupt the Hawking process and therefore totally get the same rate.
I will come back to that. The question is, can you do that? So that would be this this option. These are the two options.
It's not easy to determine it.
It's not easy, but I'm not certain that it's impossible. Don is making a face like he thinks it.
I can't remember. We had some results in one of our papers with some limitations on this. I can't recall the details right now.
Yeah,
So I'm not sure whether I'd stand by the word impossible, but it's not easy.
Granted, not easy, but maybe possible. Okay, so pressing on. Okay, so let's explore these in turn. So first, the possibility that the Bekenstein-Hawking entropy, or the black hole entropy is lower than the Bekenstein-Hawking entropy. Well, let's turn this around. Do we know that the black hole density of states is given by Bekenstein-Hawking? Well, first, what's an alternative? An alternative is that the Bekenstein-Hawking entropy characterizes the semiclassical near-horizon geometry, some characteristic of that, but we know that that semiclassical geometry doesn't give the exact physics to begin with. An extreme case of that is if we accept the firewall picture where it just the geometry completely breaks down there, and in fact, if you accept that, then there's a real puzzle about how you even end up with the Bekenstein-Hawking entropy, from that point of view. So another way of saying it is that the Bekenstein-Hawking entropy may characterize the sort of formal subsystem entanglement. In fact, there is formally a Bekenstein-Hawking entropy right here on this surface if I take a Planck scale cutoff, but we know that's not particularly meaningful, or at least it operationally isn't particularly meaningful to what's going on here. And I've already given the analogy of the sun, where you basically have different temperatures and entropies. So let's ask the question, is there any incontrovertible evidence for the Bekenstein-Hawking density of states? And the things that are usually cited are BTZ, Strommen-Dravafa, and Hanada et al. BTZ is 2 + 1 dimensional. It's rather special. We don't really, at least I don't understand the degrees of freedom of the BTZ black holes in a simple fashion. So I'm not quite sure what's going on here. Strommen-Dravafa is a weak coupling story applying to near BPS states, and there are assumptions about it extending to strong coupling. But
does the same problem arise near extremality? I mean, if you want to run your story.
Yeah, you could also ask the question exactly what happens. Well, it's also weak coupling too, though, so as well. So maybe there's an order 1 correction.
All of the SCFT came out of the fact that the weak coupling analysis of the near BPS states just doesn't work. It breaks down. And then one conjectured ADS-CFT to explain why, nonetheless, the formulas work for real black holes, because the formulas you calculate from the CFT match the formulas you get from semiclassical scattering, and we all believe ADS-CFT is right, I think. Okay.
I take exception.
You don't think ADS-CFT is
I'm
right?
not going to make that statement, that I believe it's right. And if everyone else wants to say they believe it's right, then that's fine. There's a difference. We acknowledge.
I correct myself. If I assume ADS-CFT is right, then it seems to me we have to accept
right,
near
be careful
extremal
about right.
black holes that the counting is counting states. I don't.
Well, we don't understand what ADS-CFT is telling us in many ways. And so let me just leave it at that. This is an option I think we should consider. People have arguments against it, I know, but...
Can I maybe also add to the list the success of black hole thermodynamics in general relativity?
Well, it's a beautiful structure, but it sort of had to work.
Going against your own third possible, whatever, starting point where you say you're going to be conservative and not trying to change the semi-classical physics.
I'm going to try to change it as little as I can, and maybe
this would be like a big change.
Well,
this is like 40 years of physics, right? I mean, if you throw out the BPS argument, you throw out string dualities, right?
Daniel, I'm reminded of discussions I used to have with equally bright young people a decade ago, and they would look at me and say, how could you possibly question complementarity.
No, but that's different. I mean, string duality. String duality and ADS-CFT have been checked quantitatively, in 10,000 papers, right? I mean, complementarity was sort of a story that didn't really have any equations, right?
Okay. We could debate this all night, and we don't have till night, or all day. Let me just...
Your answer to Daniel's comment about black hole thermodynamics is you believe that the laws of black hole mechanics in GR are correct within GR, and that all their constants in GR are correct. You are simply saying that they should not be fundamentally interpreted as counting the density of states of the things that we tentatively call black holes.
Yes.
I would say that, the...
Black hole mechanics doesn't give you the Bekenstein-Hawking formula.
It doesn't give you the coefficient, that's
Gives you
true.
an absolute constant.
Yeah.
But are you saying it you differ just by constant factor? Or?
A constant would do it, actually, I think. So. Okay, so I will agree that these are strongly suggestive, but
I'm sorry, Steve, so that in the ADS-CFT story, you think the 3/4 is the constant that would...
one could conjecture that. I won't...
I mean, we know how to do that calculation for sure in gauge theory at weak coupling, right?
Yeah.
And then there's this issue of the 3/4, and it's not a 2+1 dimensional model, and so on.
I'll just come back to the question of, what do we really understand about what ADS-CFT is telling us about the fine-grained structure of gravity? And there are just, there are puzzles there that I think are vexing a number of us. So, now, some still have the faith despite that. Some question the faith, but anyway, that's the story.
And the 3/4 is similar to the Hanada et al. It's the same spirit.
Well, the Hanada, I put a question mark next to Hanada et al. Because certain people here believe that in some respects, that's too good to be true, that their result. But
What's too good to be true?
The Hanada et al. Result. You can have a side discussion with Daniel, for example. But anyway. Okay, so bottom line. Well,
yeah. But no, the comment was just that the calculations are not rigorous. I mean, they cheat on the fermions. Now that doesn't mean that the answer is wrong, but it's just a little unsettling that they cheat on the fermions and still get the right answer.
There's also a funny order of limits.
Yeah, that's right.
Otherwise, the thermodynamics is not well defined.
Yeah, they have to put in this wall. Yeah.
So I will accept strongly suggestive. I will ask the question, are they incontrovertible, these pieces of evidence? And I will also ask the question, if this equality in the end implies firewalls, well, do we believe that? There's a question of what is reasonable to believe and what isn't here. And I think rational minds can differ on that. I will also say, related to the question of ADS-CFT, is if, even though we don't seem to agree what ADS-CFT is telling us, if ADS-CFT does imply firewalls, should we believe that? Good question. Okay. So in my mind, it's conceivable that this is consistent, and I've examined these arguments a little bit more in this paper. But I certainly agree, and this is related to the comment about black hole thermodynamics, it's rather inelegant, and we should explore whether there's a way around it. So that's what I'll come to next. But again, put differently, we know we have to give up something, and as we've discussed, maybe we have to give up a little more than we thought, and we have to give up the Bekenstein-Hawking formula as a fundamental count of the degrees of freedom. Okay, so an interesting prospect, I think, turning to the next part of the story, is couplings to the stress tensor, like I mentioned. But here we might notice that this is basically just like coupling to extrametric fluctuations. So the effective description of such couplings is something like state-dependent metric fluctuations. You might think of them as coming from some inaccuracy of the classical or semiclassical geometry. And these couplings are kind of nice because they mirror the universality that we know gravity seems to have. Also, I won't go into this, but this kind of coupling helps address the various mining discussions. One thing this kind of coupling can do, coming back to an earlier question about whether we can just modify the Hawking flux, these can just modulate the Hawking radiation. Say you have, on the average, a certain number of Hawking photons coming out, of order 1 per light crossing time. And this kind of coupling can, introduce extra phase shifts into that, for example. So that raises the possibility, at least, of a small, say, order 1, or perhaps even vanishing increase of the energy flux, which is worth exploring. And in fact, it can be explored, at least in a two-dimensional model. And in a simple two-dimensional model with this kind of coupling, you can, say, compute the outgoing Hawking flux to leading order in the coupling, to order 1 in what I'm calling now capital G mu nu. And you can ask what the integrated energy making it out to infinity is, how it changes. And you can actually compute this basically because you've got the exponential of this providing a source, and then to linear order you expand that, and you end up with a stress tensor two-point function, which we can just, we know what that is in 2 dimensions if we're dealing with massless fields. And you can show that, say if you have a compact support oscillating G mu nu, integrates to 0. So at this leading order level, you do, in effect, change the timing of the energy coming out, but you don't add extra energy to it.
But it seems clear that at the next order you're going to get some...
Yeah, that's a question. And at least classically, if you treat this as a classical source, there's a generic argument that you do have a next order correction. But really, you shouldn't treat it ultimately as a classical source. So one has to do a better calculation. There's a question. Okay, so we don't yet have the model for the full calculation, but this is at least suggestive that, well, at least you could have a small order 1 correction.
So Steve, I asked this before.
Yeah.
If you want to, Hawking radiation is something that we can imagine taking place in a universe that has lots of light fields, so it could be a factor of 100 bigger than it is in our universe.
Yeah.
Is a coupling to one operator enough to solve the information problem in that context?
I think so, because I think that this is a little bit like just modifying the Hawking process itself. In the Hawking process, we know if we have more fields, we have more radiation.
Yeah, but as you said, this is sort of like changing the timing of the Hawking photons.
Yeah.
But don't you change...
They don't all have to change the same.
If the coupling is just the stress tensor, doesn't that change the timing of all the Hawking photons? Regardless of their flavor, the same way?
No, because different ones are emitted by virtue of these couplings at different times.
But if you just have the one coupling
quantum
to the stress
process.
tensor, that's flavor blind. You can't tell. It has to act in the same way on the Hawking.
I think you can get different changes in phase. We could try to go through that.
I don't see how that's possible.
Well, again, it's let's think about it in a limit where this is, G mu nu is oscillating. And maybe it's very small, so the amplitude for it to dephase a given Hawking photon, or let's say a red particle or a blue particle, there are 2 kinds of particles. The amplitude for it to dephase one is small. So at one time it will dephase one, and then later it will dephase another, and they are not typically at the same time. So there's...
Okay, but you want to work in the large amplitude regime where you...
we'll come... In a sense, it's large. Yeah. So
I'm worried about the upper bound. I agree that the first order effect will scale with the number of particles, but I'm worried that the maximum amount of information you can transmit is not enough.
Yeah. This is worth trying to, address more sharply. I agree. Okay. So, so we don't have yet a model for the full calculation here because you need to take into account the fact that G is quantum, for example. How large are these effective fluctuations? And by the way, I'm not too far from being done. This is slide 14 of 17, so almost there. How large are these effective fluctuations? So, we've got some couplings. They've got a job to do. First of all, they extend a distance L outside of the black hole. Their job is to turn the von Neumann entropy curve, which is linearly increasing in the Hawking scenario, into something that's decreasing. We know how big of a change we need. We need something that's of order at least minus 1 over r to make the curve go down. So that tells us how big these couplings should be. So we're going to assume, again, for example, that we extend just the simplest case, have these couplings sort of active over a range of order the Schwarzschild radius outside the black hole. Let's suppose we're coupling to things of energies of order the Hawking quanta energy, wavelengths of order the Hawking wavelength. So what size matrix elements do we need? And first of all, these are dimension 0 operators. We need matrix elements which basically are of order 1, and then say we have some sinusoidal time dependence. This is, say, the ingoing Eddington-Finkelstein V, the radius, the usual r coordinate. And then just to model it, some envelope function which basically is telling you the effect shuts off once you get outside the blue region. Okay, so that's a simple model, but the important point here is to do this, basically you need something that's of order 1. Okay, so that's a little surprising, not if you think about it for a few minutes, but what it's telling you is that you have basically strong fluctuations, order 1 fluctuations in the metric, but in this picture there's soft fluctuations, again in the effective metric, in this effective description. So in some sense this is opening up a new possibility, a new alternative that is different than the firewall. It's not a hard structure in the, so to speak, high energy modes, but it is a structure that has a significant effect on degrees of freedom propagating into the black hole. So, you might see, one way of thinking about it, if I'm going to fall in, I might see a fluctuating tidal force. It might not be a huge tidal force because it's of order the tidal force that's already there if I fall into the black hole at the center of the galaxy, and that's small at the horizon. But it might be fluctuating. And so this could lead to even more significant modifications to the Hawking radiation. So to do a really proper calculation, one would have to do some more work. So that's what we seem to be led to with this sort of simplest form of the coupling to the energy momentum tensor. And let me just close, and this starts to get at Jim's question, perhaps, by saying that this sounds a little wild, but it comes from a chain of reasoning trying to figure out how the information could get out, and in the end, if it's true, it offers an opportunity. Namely, we are looking at the black hole at the center of the galaxy, Sagittarius A star, with the Event Horizon Telescope, which is a very long baseline with the size of the diameter of the Earth. And what do we expect to see ultimately? And they're already seeing structures on the relevant scales. Well, what is expected to be seen is shown by these kinds of simulations. And these simulations show two features. One is a black hole shadow, and another generic feature is a photon ring, this ring-like structure here, here, and here. And where the photon ring comes from is accumulations of light orbits, or geodesics, light-like geodesics near the photon orbit, which, if it were a Schwarzschild black hole, is at 3r over 2. And, of course, for Kerr, it's at a shifted radius. So this is in pretty close to the horizon and produces this feature, this accumulation of the geodesics near there. And so if this seemingly crazy story is true, you would expect that there are alterations in these images because of the fluctuations near the horizon. That the shimmering of the black hole atmosphere, say, distorts these images. And one can, given just what I've said, come up with simple models that reflect the typical size of the effect and then try to see more specifically how these images would be distorted. But the prediction is, without having detailed calculations, that at least so far, that the photon ring, for example, would be washed out. Yeah?
So it seems like there's an infinite number of parameters you could have in these models. Is there any way to make some universal kind of prediction? If all the scales are the same, there's sort of
Well, roughly a simplest thing you can do. You have some, say, sinusoidal dependence with frequency of order 1 over r, and you're restricted to a size of order 1 over r and wavelengths of order r. So there's not a lot of latitude, but maybe the scale is not exactly 1 of order r. So there are other parameters you could consider, but I think there's just a generic size that is given by the story, and that's one worth exploring. Now, of course, there's a big theoretical uncertainty, and that is, when would you expect such modifications to switch on? And we've talked about 2 timescales. The r log r timescale, which is the quasi-normal mode timescale or fast scrambling, for Sagittarius A star is about 8 hours. It's probably more like 6, but I like to think of 8. So, if that's the relevant timescale for modifications to effectively switch on, no problem there with Sagittarius A star. But if the relevant timescale for these to become effective is the half-life of the black hole, that's 10 to the 74 times the age of the universe. So obviously, those will not have turned on. So we need to know more about the fundamental theory, but at least this offers a window of opportunity, and one that is worth at least thinking about. We have Event Horizon Telescope observations upcoming. So just to conclude, I've said that the unitarity crisis, I think we all know, represents a conflict among our basic physical principles, and something has to give. This nonviolent story proposes that you have soft information transferred to the atmosphere of a black hole, and what gives is macroscopic semiclassical locality. The typical models give this sub-Bekenstein-Hawking entropy for describing the true number of microstates. But there's the possibility of special models that at least are order unity departures, or maybe even better than that. This story of effective metric fluctuations is a fairly natural and universal alternative, but leads to a story where you have more significant fluctuations than, or at least significant fluctuations, let's say, although soft ones. So it's different from the firewall story. And those could present an observational opportunity. So I'll stop there. Sure.
So do you avoid the sort of the information theoretic argument of the firewall paper in terms of sub-additivity constraints? If you have this kind of comment? Or even if you take the SBH smaller than whatever Bekenstein-Hawking interval, can you then avoid the information theoretic arguments of the firewall?
At least at the sort of first pass level, I think so, because basically these couplings are transferring information out, or entanglement out, and in that sense they're doing much like what you ordinarily expect of other physical systems. As the system shrinks, the information comes out. So they're not doing anything from that point of view too wild. Now, so I'm not sure which version you're worried about.
Well, I mean, Samir had this argument that you cannot do small corrections.
Good. Yeah, and they're not. You do have to have there's this benchmark rate. You have to have of order 1 qubit per light crossing time. That's the scale coming out. And so you need to achieve that. You can't do that by just having a small perturbation of the Hawking state for, say, each Hawking quantum. You have to have a more significant change. That's all. So, Jim.
Could you say a word about causality? If a neutron star binary collapses and makes a black hole next month,
yeah,
right? Do I have to add a piece to my Hamiltonian now for next month? Or?
Maybe after r log r.
R log r.
Where that's the Schwarzschild radius of the resulting object. That's at least one possible. If we're trying to parameterize our ignorance, that's one guess.
Well, here I am doing observations.
Right.
Local observations. I don't know anything about the black hole. I'm just looking at my field theory.
Yeah. So the effects are small for neutron stars, and they switch on, say, on a time scale of order.
But they make a black hole.
Yeah, you make a black hole, and then they switch on a timescale of order r log r. So here, never mind neutron stars.
My question is, what frame are they switching
The black hole frame. Here's your neutron star, and up here, this is at least one proposal. Up here, they switch on after this has been around for a timescale of order r log r. That's sort of the
over a whole space-like surface?
No, because they're switching on in the immediate vicinity of the black hole, and that's a scale of order r. Say. And again, it could be longer. It could be r cubed, in which case, at least forget it for observation, right? Well, unless we find primordial black holes or black holes at the LHC or something. What's that?
No problem with the Redson.
No, I don't think so. Again, because this process sets a frame. There's a frame there, and the physics could use it. So, yeah.
So maybe I missed this point, but so if I think of the black holes in ADS, is there completely no consequence of adding this term, or it's not there?
That's sort of a question related to what's the equilibrium story, and that should be thought about more. I agree. Whether or not we say that ADS-CFT gives the correct predictions, it's an interesting theoretical laboratory to think about what the story would be in ADS. So, as I've said, at least if we end up with this story, it looks like in the end the story of the microstates of the black hole modifies at some level the usual geometrical picture. Samir.
I was just having fun trying to see what it might do to an accretion disk around the hole. I was making a toy model for myself while you were talking. So suppose I just imagine is this the kind of thing you might think of doing? Suppose I increase the metric just outside the hole on the time scale of each Hawking pair, which is like a crossing time. I make it go up and down just sinusoidally.
Yeah.
So if I have an accretion disk which ends at the last stable orbit, suppose the metric goes up by 10%, down by 10%. Yep. Each time it will swallow 10% of the disk, which will, I guess, become unstable fall in.
Yeah.
10% more. So
bottom line is, I think it can lead to additional instabilities at the bottom if it extends out to the accretion disk. You have an accretion disk, but then inside that, basically free streaming. But if the effect has a significant effect out to here, then it could lead to additional instabilities in the accretion disk.
So the very simple model you can just imagine is that orbit was stable, but now the metric slightly increases, so this much becomes unstable, so that part gets eaten.
Well, or one,
slowly the whole disk would just vanish, right? In an hour or so.
The whole what?
The whole disk would more stuff falls in, it just come in.
I don't think the whole disk vanishes, but I talked to people who study accretion disks about this. And this is the bottom line story was complicated magnetohydrodynamic problem. So, and not absolutely obvious, but what in the end happens. But it's a source of additional instability because if you just had orbiting particles, they're going to fall in faster, generically. If you start, you don't have the stability of the orbits if you start doing this. So, on the other hand, there are things I think that we don't understand about the detailed dynamics of accretion disks at those scales, in terms of observation versus the theory, at least is my understanding that, there are still puzzles there, in fact. Yeah.
I just wanted to make a comment on the second one. So, at least in the quantum information apps, there's an abstract setting in which you can transfer information without ever coupling two subsystems. It sounds wrong, but it's true. And there's a necessary and sufficient condition for which you can know whether this is possible or not. And
you couple them somehow.
I mean, I know it sounds wrong, but this is possible.
You mean like signaling where we want to send a signal? So say we.
So more precisely, you want to send part of your system to this other part.
Yeah.
Yeah, that's. In certain settings, you can do that without ever coupling these two systems.
Talking about teleportation?
It's a more general version of that.
But don't you have to still...
so you have to send something.
Not teleportation, actually. So what you do is that you perform some local operation. So before you start the protocol, you first specify the rule on what you're going to do. So Alice does some local thing, and Bob does some local thing, and then.
But the two systems are in an entangled state.
They are in an entangled state. Yes.
And you have to communicate. There's some form of communication that has to take place.
There is no communication.
Then how do you transfer something?
Well, it's not exactly transferring information, but you're transferring the subsystem. So you have a
transfer of subsystem is still, it's a different version, I think, of the same kind of thing.
So the formal version is this. So Alice has 2 qubits, and Bob has 1 qubit, and some qubit that is set to 0 state, for example.
Yeah.
And Alice wants to send one of this qubit into this Bob's Bob's 0 qubit.
Yeah. Okay.
And under certain settings, Alice can just do some local operation. Bob can just do some local operation, and you end up having Alice just having a 0 tensor product, one of Alice's qubits, and Bob has Bob's original qubit together with the qubit that the Alice initially had.
That sounds like it would require an operator that basically does accomplish an interaction. So I'm not quite sure.
No, it's the interaction is through the initial state. It has to be in some special initial state.
Okay.
If the initial state is chosen in order to transfer a particular final state, or you can choose this state of the qubit to be transferred independently of the initial state.
Otherwise, you're not transferring.
This is my question.
Sorry, can you repeat the question?
If
Alice wants to send qubit 1 to Bob. She wants to send qubit up. Let's send the message
But
up.
do you know that it's up already?
You don't know it.
you don't.
Otherwise, it's
So
not
you
a
can
qubit.
prepare your state and then decide later what thing you want to transfer.
I guess. Sounds like something where we ought to see the simplest model of this on paper. So, yeah.
I still tend to, in the sense that this kind of suggestion does kind of should be interpreted as anti-firewall, because if you say that it is soft, then or maybe it still allows for some short distance appear.
Well,
so what would be your interpretation of this?
Well, the problem of singular horizons, if you try to transfer to the modes right at the horizon, by the way, was appreciated all the way, way back, and people have written about it, including myself in print, going back to 1980s or something. So the idea was to avoid that, to avoid singular horizons that come from transferring to the degrees of freedom right at the horizon. And in fact, that's what the first version of this I proposed was, before it got called a firewall, but was trying to avoid that scenario.
Could you comment on the possibility of modification of gravity in the deep infrared? Let's say, for example, giving up the notion of derivative expansion of effective Lagrangian and possibly giving up the notion of class-based S matrix.
Yeah, I think they're sort of, if you're doing something like violating locality or local quantum field theory, there are different sort of levels at which you can do that. And, you could, characterized in different ways, for example, by the scales over which you are thinking about violations. And this is trying to be sort of most conservative and assuming that, really there's not a big modification of local quantum field theory, say, asymptotically for states that don't look like black holes, saying outgoing degrees of freedom look like field theory degrees of freedom. And so, if we're trying to be conservative, I think that's seems like a sensible way to approach it.
But from an observational point of view, it sounds like it would be more reasonable to modify GR at the Hubble scale than at the near large black hole.
Well, except that does not help you with what appears to be a conflict between our fundamental principles. That's the problem. At least it's not obvious how it does. Yeah.
If the action has non-local and time stuff, then that sort of corresponds to an infinitely high order and time derivative action. Tends to be unstable.
Yeah.
I guess I'm curious why you wouldn't have proposed, that there's actually a preferred foliation that modify the Hamiltonian on.
Let's back up. A real possibility, it seems to me, is that the underlying fundamental description is not the field theory description. Okay, so the whole, field approximate local quantum field theory story is just that, approximate. And so we have some more fundamental quantum dynamics, but we should be careful not to push the local quantum field theory description too far. And so this strikes me as a question that could get into that territory.
I interpreted your conservative plan as being that you would continue to use quantum field theory, but you would just modify it by a non-local term in the Hamiltonian or something.
Yeah, well, again, that's a phenomenological effective model, so there are key words there. That's not the fundamental description, because it's hard to turn that into a fundamental description, I think.
I think Ted is asking something else, which is, you can probably pick a nice foliation, write down not an integrated,
for the black holes.
Not a time-integrated Hamiltonian, but a Hamiltonian, which is spatially non-local on this set of slices.
Yeah, okay.
That seems like it's not the same as what you were proposing.
No, it is, because there's a, it depends on, let's choose some slices. Here's a slice.
That slice, I don't understand that slice.
That's a nice slice.
You're going back out at the other.
You're worried about, sorry. Let's say it asymptotes to constant r. These lines are not, anyway. I didn't quite get it right. It asymptotes to constant r. Then it's a nice slice. And so if it's something where it goes from here to, say, somewhere out here on this slice, then, actually that's one of the issues with the nice slices is there's a degeneracy. The slices all match up here. So, but the point is, I think that you're not doing something that's sort of non-local in time out here. And what you're doing in here is in the region where you're not supposed to be trusting local quantum field theory anyway.
So your proposal is equivalent to doing a spatially non-local Hamiltonian on the nice slices?
Again, I'm not thinking of the stuff inside as described by local quantum field theory.
Okay, you can cut off the nice slices.
So it's going from in here, and so let's say I'm not going to talk about slices anymore inside here.
Fine.
It's going from in here to out here.
Can I now write down a Hamiltonian, not an time integrated Hamiltonian?
Yeah.
A Hamiltonian which involves spatial integrals on the outside part of the nice slices and operators that live inside.
I think so. Yeah, I think it's just you strip off the t, the dt in the expression I had.
Well, you have to know what frame we're stripping off the dt.
Yeah, so pick a slicing, strip off the dt.
But we have to decide what the slicing is, because if I pick one and you pick a different one, then they won't be the same.
So there's some, there's a background here and there's background dependence, and you could write it, I think, in different.
It's also slicing dependent.
Let me see. Sorry. It's integral. It's of the form integral d4 x, and then your operator, but then something of the say a coupling function times operator. This depends on x. And so that is, from the outside point of view, that's the interaction. It's like having a source. And you can slice it different ways outside.
It's a time-dependent interaction.
Yeah, there's explicit x and t dependence in here.
I guess I'm I guess my version of Ted's question is, can we specify that T dependence a little bit?
Yeah, so one can give models for that, for example. The question is, in the black hole states, say, what do the matrix elements of this look like? And, there's some functions that depend on the state and on the black hole. And you can write down, candidate functions. And they're going to look like different functions in different coordinates, of course, but they're in that sense just functions of, say, x, r and t, and omega. Samir had one more, and then, we should wrap up.
I was just wondering if, given how similar the black hole singularity is to expanding cosmology, would you allow me to apply the same thing near the Big Bang and maybe find extra correlations in things like inflation, which I could,
Yeah, this is a really interesting question. There are things that are the same, sort of superficially the horizon structure, and there are things that are different between cosmologies and black holes. And so this is a really good question, and I think it's a question where we just have to understand more of the fundamental dynamics, but it's worth thinking about. So. Okay, well, I'll put on my coordinator's hat, and it's 12:30.